Yesterday we did reciprocal graphs, and we're going to use what we learned yesterday to do cosecant, secant, and cotangent graphs. So a review of reciprocal graphs. You graph the bottom function first. So in this case, we would graph sine theta first. Once you have sine theta first, then you go through all the steps for reciprocal functions, which is asymptotes. Wherever you have an x-intercept, you're going to draw an asymptote. If your graph goes off to infinity, you have an asymptote at y equals 0. And then we just take a bunch of nice points and see what happens. So here is the graph of y equals sine x. If we wanted to graph cosecant x, which is 1 over sine x, our reciprocals say, well, wherever you have an x-intercept, that's now a non-permissible value. So all of these x-intercepts are asymptotes. And there's lots of them. But the sine graph doesn't go up forever to positive infinity or down forever to negative infinity, so we don't need to draw an asymptote at y equals 0. There will still never be an x-intercept in a 1 over graph. So there are no x-intercepts, but we don't need that asymptote at y equals 0. Then if we think about points on the original graph, so like I have pi over 2 comma 1 here, and I have pi over 6 comma 1 half. Just a reminder, your unit circle and your pi plate, they'll give you a blank one on your exam, but we do have to have that memorized again. So that's something to prepare for your exam. Make sure you know your unit circle for your exam as well. Now, if I do the reciprocal, remember the reciprocal just takes your y value and makes it 1 over that. So pi over 2 comma 1 is going to stay pi over 2 comma 1. Pi over 6 comma 1 half, well, the reciprocal, 1 half's reciprocal is 2 over 1. If you did 1 divided by 1 half, you would get 2. So we have the point pi over 6 comma 2. And technically, since you know it has to go towards the asymptote, and you know it can't have any x-intercepts, it has to go up towards the asymptote. And in fact, that's going to be the same for every section where it's 1. These will all be up towards the asymptotes. Now, if you took a point like -1 and did 1 over -1, it would also stay the same. So all of these minimum points are also going to stay the same, and this section is going to go down. And this is the graph of cosecant. So I would like you to try to do the graph of secant on your own. Secant will be the next one. And then when we get to cotangent, cotangent's a little bit messed up. So it has some special rules. Did you have asymptotes at each of the x-intercepts? Then wherever it was 1 over 1 would stay the same. And these sections would all open up. And wherever it was -1, these points would all stay the same. So just like the sine and cosine graphs look very similar to each other, the secant and cosecant graphs look very similar to each other. And now we get something interesting with cotangent. Cotangent kind of follows the rule, but kind of doesn't. And it all stems from the fact that in identities, you learned that cotangent theta was 1 over tangent theta. In identities, you also learned that cotangent of theta was cos theta over sine theta. Now this poses an interesting problem because if I go to my calculator, and I've got it up here already, if I do 1 over tan of pi over 2, that's not possible because pi over 2 is, on your unit circle, undefined for tan. So you can't do tan of pi over 2, you shouldn't be able to do 1 of tan over pi over 2. It's not allowed. But if I do cos of pi over 2 over sine of pi over 2, I get a number. I get that it's equal to 0. So this is the question. What is, if this is the only, like I don't have a cotangent button on my calculator. So if I want to find out what is cotangent of pi over 2, should it be undefined or should it be 0? Should it be the cos over sine, or should it be the 1 over tan? What do you think mathematicians decided was more powerful? And they decided that they would go with this. Which kind of messes us up because I want to graph it right now. And I know a strategy for graphing 1 over tan, but I don't have a good strategy for graphing cos over sine, other than dividing two graphs and seeing what I would come up with. So for graphing cotangent, we're going to use the ideas of 1 over tangent, but we're going to find out that wherever tangent was undefined before, so wherever we have asymptotes, if we deal with it as cos over sine, all of these will end up being, here I'll do it in blue. These will all be x-intercepts. Which is kind of interesting. So even though tangent is not defined there, cotangent is. Because we think of cotangent as cos theta over sine theta, not officially as 1 over tan theta when we do its graph. But we can do the rest of the reciprocal stuff with 1 over tangent. So I've drawn tangent. Wherever I have x-intercepts, I'm going to have vertical asymptotes. Because wherever I have x-intercepts for tangent, I also have that sine theta is equal to 0. And those would be non-permissible values for cotangent, no matter what. Next, on your tangent graph, you would have the point pi over 4 comma 1, right? Because tan of pi over 4 is 1. So on your cotangent graph, you'd have cotangent of pi over 4 is also 1. Because you just do the reciprocal, you get 1 over 1. So I'm going to go on my graph, and wherever the y value is 1, those points would stay the same. And similarly, wherever the y values are negative 1, those points would stay the same. So we've done our asymptotes. Normally, you would think there should be an asymptote at y equals 0 because the tangent graph goes up forever. Okay? In this situation, because we think of tangent as cotangent as cos over sine, and we've drawn in those x-intercepts that would have been on the asymptote, the graph of cotangent doesn't have an asymptote at y equals 0. And with these points, we can draw our graph towards the asymptotes And the cotangent graph has a very similar shape to the tangent graph, just going down in the opposite direction. And I would say in the last 20 years, about 40 exams in the last 20 years, I've seen the cotangent graph come up twice. It's pretty rare, but it has shown up on the exam. If I was betting this exam, I would say it's probably not going to show up. But 2 times I would have done that bet every single year, and 2 times I would have lost. So it's possible that it could come up, but it is unlikely. So if we wanted to actually graph y equals 1 over 10, instead of x-intercepts, it would be exactly the same graph with holes in the graph. Which is kind of interesting, but not that important. Question?
Yeah. When did it show up twice?
Not on the same exam.
Yeah.
But like,
were they
dispersed? Like 2008, I think I remember seeing, and maybe around 2015, 2006.
Okay.
So we're probably due for another one.
Might be due for
another cotangent.
Another cotangent graph. I don't know.
So the patterns have all been thrown off by COVID, so who knows, maybe we'll see
I mean,
for another couple of years.
Yeah. If you graph y equals, clear this out. Cos x over sine x. And get your cotangent graph. Those are our reciprocal graphs. And we have one more topic. And our last topic is absolute value functions. Now you can either take out just a piece of scrap paper or loose leaf if you want. If you have your book here, page 323 is an empty page that you could write this in. And after this, we will have learned 3 special transformations. We have learned these 2 already. And the last one of the special transformations is the absolute value. We could have put all 3 of these in chapter 2. We could have put all the special transformations together. We decided to do the square root of f of x in chapter 2, and we're doing these other ones now in chapter 4. But they all sort of have some similar patterns. Okay? Just like before, we're going to graph y equals f of x first. And all of these special graphs did something to the y values. Like for the square root graph, all you did was square root your y values. That's what square root of f of x does. For your reciprocal graph, your y values changed to 1 over 1. And so for your absolute value, all we're going to do and there's some very nice and easy patterns that happen with this. So we're going to look at those patterns. And this is our last topic. Does it make sense that if you did the absolute value of f of x, if all the y values are changing to the absolute value of y, that your entire graph will be above the x-axis?
Yep.
Okay. So here's our first example, okay? Given f of x equals 2x plus 3, we want to graph the absolute value of f of x. And we're going to do it with our new technique. So our new technique is one, we're going to graph y equals f of x first. And I'm going to put in brackets, it's going to be really important that we label the x-intercept. So 2x plus 3, that's y equals mx plus b. You're going to have a y-intercept at 0, 3. A slope of 2 means down 2 over 1, down 2 over 1. And I'm going to have my x-intercept right there. I want to label that x-intercept. We can find an x-intercept by plugging in 0 for y, and we get the point negative 1.5 or negative 3 over 2, 0. That's our x-intercept. We can now graph y equals the absolute value of f of x. Oops, that's not y. By just taking some nice points. Does it make sense that the point 0, 3 will change to, or wait a minute, 0, absolute value of 3, which is 0, 3. It stays the same. In fact, our x-intercept negative 3 over 2, 0, when you take the absolute value of 0, it would stay the same. I hope it makes sense to you that this section of your graph, where the y values were already positive, will stay positive and be identical to what it was before. But any point, like for example, on the blue graph here, I could label, if I plugged in negative 3, I'd get negative 3, negative 3. If I chose that point, does it make sense that it would change to negative 3, positive 3? Because the absolute value would take that y value and make it positive. Algebraically, what do you do to a negative number to make it positive? Multiply by a negative 1. If your y values, now we're going to go back to chapter 3. If your y values are getting multiplied by negative 1, what did that do to our graph in chapter 3? That was a flip. That was a reflection. So our entire graph where the y values are negative, they're going to get multiplied by a negative 1, which is the flip, which is a reflection, and our graph will flip up and be like this. And I think this new technique is way better than our old technique. Okay, I'm going to remind you, we could have done, show you in purple here, we could have done this from chapter 3. This is a valid question right from the beginning of the year. Can you see that your parent function is the absolute value of x, and you have a horizontal compression and a horizontal translation? But then you would have had to remember from chapter 3, anytime you have a horizontal compression and horizontal translation, you have to write it in factored form, which we always forget. So we're going to multiply our x values by a half and then move 1.5 to the left as our vertex of our square root. 1.5 to the left matches up, right? But I think this is actually a lot more work than just graphing the inside and taking the bottom part and flipping it up. Our new technique, I think, is even easier. Yes?
Does it matter which one you do on the exam?
No. Generally, though, if it's written this way, they're leading you towards the new method. Because they're saying, hey, we want you to do the absolute value of it. If it's written graph this, I really think you have choice of either one.
Okay.
You would be like, yeah, I either recognize this as the absolute value graph with transformations, or I'm like, well, absolute value of anything, graph the inside first and flip up the negative part, and you're fine. Okay? Yeah, just like the square root graph technique, I think the square root graph technique ended up being easier than the old technique. And what's nice about it is you can use this technique for any function inside, not just lines. Whereas in chapter 3, you could only do lines because we had a parent graph of absolute value of x. That was the only absolute value parent graph we had. But I could take something like, here's our second example, I could take a graph from chapter 1. Right? This is a polynomial graph. Do you see that this would make an x cubed graph with its n behavior looking like this? It's in factored form, so I would know my x-intercepts are at -3, 0, and 2. And I want to graph absolute value of f of x. So first of all, I would graph f of x. I'm going to just say, once you had those x-intercepts, and you knew its n behavior ended here and here, each of those x-intercepts has a multiplicity of 1. So it starts down here, go straight through, go straight through, go straight through, and you would be done. Now the absolute value, I'm going to graph in green. Well, we take our nice points. In fact, anywhere where the graph is positive, the y values are positive, that's going to stay the same. So those sections would stay the same. But this part that's below, if you absolute value it, you multiply it by a negative, that does a flip. And this part here below would flip up as well. And our final graph is all above the x-axis. And then, sometimes on the exam, they give you one of these special transformations, either the square root, the 1 over f of x, or the absolute value of f of x, and add a transformation to it. So I'm going to show you an example of that. We'll make example 3 here. Graph the absolute value of the square root of x minus 2 minus 3. Can I just combine the minus 2 and the minus 3 together? No, those absolute values are a function. So we are going to think of this. We want to graph absolute value of some function f of x minus 3, where f of x is the square root of x minus 2. So how do we combine our new special functions if we have additional transformations afterwards? Well, ask yourself, if the minus 3 wasn't there, could you graph the absolute value of something? Yes. If this was just something minus 3, what do you do when you do a function minus 3? It's just a vertical translation 3 down. So if you knew what this graph was, you could just shift it down 3. Now we're going to put those ideas together.
If it shifts down below.
It'll be below the x-axis in the end.
Okay.
Which makes sense. Like this on its own by itself is above the x-axis. But if you take something that's above the x-axis and then move it down 3, part of it could now be below the x-axis. But this causes what your question is great, because that's the main issue that students had when they got onto an exam and something this came up. They'd be like, uh-oh, is this allowed? I have points that are below Just because you have an absolute value doesn't mean everything has to be positive, especially if you add stuff after that. Okay, so what we're going to do is we're going to start off with, in blue, I'm going to graph y equals the square root of x minus 2. Well, that's just my square root graph. My square root graph shifted down 2 units, so I would have 0, negative 2. 1, negative 1. Very important to label your x-intercept. X-intercept is at 4, 0. Then in green, I'm going to graph what does the absolute value look like. Well, 0, negative 2 would be 0, 2. 1, negative 1 would be 1, 1. And for 0, my x-intercept stays the same. Now this part of my graph would stay how it is, but the part below gets flipped up. And finally, in purple, I can now graph the absolute value of f of x, which is the absolute value of the square root minus 3 And so, what's going to happen to 0, 2? It's shifted down 3. It's at 0, minus 1. 1, negative 2. 4, negative 3. Still has this shape in the end. So if they combine ideas that you've learned from different units, just take each thing that you've learned from a different unit and put it together and it'll be fine. It just might, like in this example, it looks a little bit different than what you would expect, because most of it's negative now. Right? Sometimes I feel like, are you just trying to mess with them? I've seen this sometimes. Okay, you know how to do the absolute value? Just throw a negative in front. Can you see that everything would be negative then? Which really bothers a student when they see the absolute value. They're like, okay, everything's positive, and then you throw a negative in front. Like, whoa, now everything's negative.
And now you flip the entire thing.
Yeah, first of all you do your absolute value, which would flip it up like the green part, and then you would take this whole green part and flip it down to get your final graph. If you have questions like this and you're uncomfortable with how it goes, remember, you always have your table of values. Like, what happens if I plug in 0? Well, 0 minus 2 would be negative 2. The absolute value, make that positive 2. 2 minus 3 would be negative 1. Do I have the point 0, negative 1? So your table of values, don't forget how powerful that is. If you're unsure on a graph, you can check things with the table of values. If your table of values in your graph is completely different, that means something went wrong somewhere. And you might be like, you know what, I'm just going to trust my table of values. And there was a reciprocal graph. I'm trying to remember exactly how it looked. there was a reciprocal graph with a transformation. I think the exam question looks something like this. Graph this. Okay? Students that tried to do it with transformations, this is really if you make f of x, x squared plus 1, this is really equal to negative 2 times 1 over f of x. So you'd have to do your 1 over f of x graph and then do a vertical stretch and vertical reflection. And almost everybody who tried to do it with the techniques that we learned in class got it wrong. And the students that went, I'm just going to use a table of values, almost all of them got it completely right.
When in doubt, table.
Yeah. Because I think the question, it was not a nice question. I think it was this. What's the range of this?
Yeah,
Oh.
I would enjoy that.
How would you define the range of that?
Draw a graph. So if I was drawing a graph with a table of values, what happens when I plug in 0? I get negative 2. What happens when I plug in 1? 1, negative 1. What about negative 1? Same thing. Can you see that because of symmetry, it's going to be the same on the left side as on the right side because of the square?
So
Students be like, oh, the degree is bigger on the bottom, there's got to be an asymptote. This graph, just by doing a table of values, is a pothole graph with a range of negative 2 included, 0 not included. Or, I could write it this way. Oh, you did it right.
not
There we go.
zero here.
Nice. Recap.
You know,
How do you know when something crosses the horizontal asymptote and when it doesn't?
So the only way something is going to cross a horizontal asymptote, in what we've experienced, there's more things that can come up, but what we've experienced is when you would have something, the degree is bigger on the bottom, let's say x squared minus 9, but on the top I have an x plus 1. Okay? I still have an x-intercept at minus 1. Because if you wrote this in factored form, you have non-permissible values at 3 and negative 3. They don't cancel out, so they're going to be vertical asymptotes. The degree is bigger on the bottom, so you have a horizontal asymptote at y equals 0. But you still have an x-intercept at negative 1, because that would make the top of the fraction equal to 0. So you have a point on that asymptote.
Okay.
Therefore, your graph is either going to bounce at that point or go straight through. Since this one has multiplicity 1, it would actually go straight through at that point. So your graph is going to have, if we look at it, right, if I just get my calculator to show us what this graph is supposed to look like, sure enough, it still has that asymptote there, but in the middle it went through.